Okay, before we begin learning how to solve exponential growth and decay problems, we have to have a little bit of background. This is a little topic that used to be taught in Algebra 2, but since we switched over to the new curriculum, it's been dropped from the curriculum. So I'm going to teach you, it's a simple concept, and I'm going to teach it to you now, just so that you have it, because we're going to be using it over and over and over throughout this lesson. So the first thing is to understand what you need to write when you see the phrase of something like y varies directly as x, or the phrase y is directly proportional to x. And if you see the expression y varies directly as x, or something varies directly as something, that's a different way of saying those two things are proportional. So this and this are two different ways to express the exact same concept. A lot of times you won't see the word directly. You'll just say y is proportional to x. If it just says y is proportional to x, it means directly proportional. And whenever you see something is proportional to something, here's what you write. You write for whatever this is, in this case it's y, equals, and then proportional to means k times x, where k is the constant of proportionality, or if you're using that wording, you would say the constant of variation. But it's important to know that k is a constant. So when two things are proportional, one is just a constant multiple of the other. It's the definition of proportional. So two things could be directly proportional, but they could also be inversely proportional. So for this, you would either see y varies inversely as x, or y is inversely proportional to x. Whenever you see that two things are inversely proportional, that means that y, or the first thing, is k over x. So two things that are directly proportional, the constant gets multiplied by the other thing. When they're inversely proportional, the constant gets divided by the other object. So y equals kx for proportional, y equals k over x for inversely proportional. Okay, this is a basic setup that's going to lead us into how we write our differential equations for all of our word problems. All right, everyone got the basics? We're going to switch now to your handout, which I'm going to put up on the overhead, and we're going to jump right in with exponential growth and decay applications.
You have 24 subscribers.
Oh, that's nice.
Yeah. And your username is just Addis Price.
Oh, good. That's good to know. I honestly did not know my username. So that will come in handy.
Now you have 25 subscribers. You're welcome.
You don't subscribe?
What? I just subscribed.
She has 24 now. I should just remember to make it 26.
All right. So here's our first example. The rate of increase of the population of a certain city is proportional to the population. If the population in 1930 was 50,000, and in 1960 it was 75,000, what was the expected population in 1990? All right, so, how would we know? Well, let's talk about how we set this up. This first line is the basis for almost all regular exponential growth and decay. And this is what we're going to use to write our differential equation. Excuse me for 1 second.
Let me get it.
Okay, so the rate of increase of the population. So if I just start with this first part, the rate of increase of the population. If I call the population P, and ignore the word increase, whether it says increase or decrease, think just change. The rate of change of the population, or in other words, the rate of change of P. How would I write that in mathematical notation?
Delta P.
That was beautiful. Beautiful. Okay, rate of change of the population, and it doesn't say instantaneous, but that's what it's kind of implying. So you're right with the delta P, that's change, right? Don't be ashamed, that's good. So rate of change, see, it's the beginning of slope, right? It's leading into slope, which we're going to, in this class, we're going to use the derivative. So the rate of change of the population is dP dt. Now the reason it's dt is because if I asked you, hey, what rate is this population changing at? Well, you would usually, in units, you would say people over some units of time, right? In this case, it would be years.
Export of bananas.
Okay? All right, so dP dt. So the rate of increase of the population, that whole thing, that's dP dt. All right, do y'all understand that? Okay. In math, what does the word is mean that you write with the math?
Equals.
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 Okay? So the rate of increase of the population of a city is proportional to. Whenever you see the words proportional to, if they don't say directly, they mean directly. If it just says proportional, it means directly proportional. So whenever you see the words proportional to, you're going to write K times. Now, what is it proportional to? It's proportional to the population. What are we using for the population?
P.
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 dP dt equals Kp. Alright, dP dt equals Kp. Now, this is a differential equation. We need to solve it. There are only two variables in this equation. What are the two variables?
P and T.
P and T. Is K a variable?
No.
No, K is a constant. So the K, and the K you want to keep on the right-hand side. When we separate the variables, we're going to put the P's on the left and the T's on the right. And you're thinking, well, the K could go either way. Keep the K with the T. Because if you move the K over with the P, you're going to have to do a U substitution. So if you want to keep the U substitution out, then just keep it over here with the T. So here we go. When I'm going to divide by P, so I get 1 over P dP equals K dt. I guess you could pull out a 1 over K and treat it as a coefficient too. Either way, it's just easier. Keep it on the right. Keep it with the T's. Think KD, right? KT. Okay.
There's an E in there.
All right, except there's a D.
KD.
Okay, KDT. All right, so now we have to integrate both sides. What's the antiderivative of 1 over P dP?
Absolute value P.
ln absolute value P. I am not going to write the absolute value. Why am I not writing the absolute value?
You can have negative.
You can't have a negative population, right? Okay, you were asking the other day, and I'm going to go ahead and let this be on video. You were asking the other day about classes that are memorable. There was one class that was really memorable, and the reason that this one class was memorable was because when I said I don't have to put an absolute value around the P, and why not? And they all said, oh, because you can't have a negative population. One of the kids, the timing is so important on it, right? Because it was so immediate. Goes, well, you can't if they're zombies, right? So then this led to this whole discussion of, Well, what would happen then if you had,
Well, you have the population zombies.
right, so if you had, like 10 people and 10 zombies, does that mean your population is 0? And they immediately said no, because within a couple seconds you'd have 20 zombies and then your population would be back to negative 20, right? And so we had this whole talk about negative population and could we apply it somehow to calculus. So it's something to think about, right?
That's so cool.
Yes, but right now,
You could have negative growth.
yes, right now, we're gonna stick with a positive population.
Maybe if there's like a negative dimension, then it might be possible.
Right, okay. So anyway, on the right, ooh, what's the antiderivative of k with respect to t? Beautiful, all right? The antiderivative of k with respect to t is not 1/2 k squared, because k is not a variable. K is a constant. Think of it like 5. What would the antiderivative of 5 be with respect to t? It'd be 5t. So the antiderivative of k with respect to t is kt plus c. All right, I need to solve for p. What am I going to have to do to both sides? E them. Yes, I have to exponentiate both sides. E to the natural log of p is just p. And on this side I get e to the kt plus c. I'm going to skip a little step here. This is e to the kt times e to the c. And e to the c is just a constant, so I'm going to call it, I always call it ae to the kt. My first period made me write me to the kt every time. Whatever you want to do, all right? Whatever letter you want to go with. So today I'm going to use ae to the kt. So if we start off with the formula p equals ae to the kt, does this formula look familiar in any way to any formulas you have learned?
Never.
It does look like the exponential growth formula. Does anyone know what that formula normally is written as?
RT.
Yeah, PERT, right? P e to the RT, and remember the PERT formula? No?
I remember Pivner,
That's
terrible.
Oh,
The ideal gas law, Pivner.
okay, well, PERT is for any natural exponential growth or decay. They all fall under the PERT formula. It also is for continuous compounded interest, right, in banking? Okay, so PERT is the formula that you use for any natural exponential growth or decay. If you're using PERT, which we're going to call ADT, right? This ends up being your initial amount. P was, in the PERT formula, P stands for principal, right? It's the initial amount. And then the R here is your rate of growth, right? And the T is time. And this is your outcome. So in this case, we're not going to call it PERT, because P stands for population. So we just call it whatever it ends up being. But just know that that is how the PERT formula is actually derived from scratch, right? Okay. All right, so now we've got that. Now we have to actually solve the problem. So let's look at what we're given. So I'm going to make a little T-chart. You don't have to. This is just my thing. So in 1930, watch out because I'm going to erase, so don't freak out. In 1930, the population was 50,000. And in 1960, the population was 75,000. And we want to know what is the population in 1990. So we have two unknown constants that we need to solve for in order to get a real function that we can use. Because when we have a function, we just need an input and an output. We can't have any other unknowns in there. So the unknown constants are a and k. Right? Those are, e is a known constant, right? P and T are variables, A, E, and K are all constants. This one is we know, this one we don't know, and this one we don't know. We got to figure them out. So we have to find our constants first, so we get a formula where we can just plug values in for T and get an output. But in order to do that, we need points. You have to have at least 1 point for every unknown. So we have 2 unknowns, we have 2 given points, which is nice. So here's the thing. I don't want to plug in 1,930 for T to get my 50,000 population. So I'm going to take a little step and I'm going to say, you know what? I'm going to let 1930 be T equals 0. And I'm going to measure time as years from 1930. Life is always easier when you have a 0 starting point. So if 1930 is 0, what would 1960 be?
30.
And what would 1990 be?
60.
Okay. Much easier to work with. You can keep the years, but it's much easier to work with if you reset your t-values. All right, so here we go. I'm just going to plug in. So my population is 50,000 when my t is 0. Hey, e to the 0 is just 1. So that means my a is 50,000, which makes sense because this is always the initial value when you're using this formula. So now I have p equals 50,000 e to the k t. Now I plug in the next given set of points. So I have my population is 75,000 when my time is 30. So I have e to the 30k. All right, how do I solve this? Divide by 50,000, so I get 3 halves
Take the natural log.
equals e to the 30k. How do I solve an e equation?
Natural log.
Take the natural log of both sides. ln 3 halves equals 30k. So k is 1/30 times the natural log of 3 halves. Don't put a decimal for k. If you absolutely have to, which is rare, but if you absolutely have to put a decimal, you need to write every single decimal on the screen. You cannot just round k to 3 decimal places because your answer will be way off. Because remember, we're talking about answers that are getting multiplied by 50,000. So if you have something that's correct to the nearest thousands, but you multiply it by 50,000, now you're off. Like, you're only going to be correct to the nearest tenth, not even close to the nearest thousand. So you've got to have like a quadrillion decimals for k if you are going to round it. So your best bet is keep k exact. Okay? All right, so here's our final function. P equals 50,000 e to the 1/30 times natural log of 3 halves times t. All right, we've got a function. Now we can actually solve the problem. For all of these problems, the final thing of solving the problem is the easiest part. So now how are we going to find out the population in 1990? Plug in a 60 for t. Now here's the trick. If you have a calculator, I want you to actually try this because it took first period at least 3 or 4 tries to get a correct answer. Because it gets so confusing with all the parentheses and everything. So you might want to practice to make sure you can enter it correctly. These are some of those types of problems where you probably won't be able to leave your answer like this. You probably have to give a number, because a lot of times what they'll say is round to the nearest person, that kind of a thing. So you can't just leave an unsimplified answer. Usually you have to give a number.
Is it 112,500?
It is.
These calculators are like literally the easiest thing to do.
They are.
Yeah.
Those are nice. Yep.
Hashtag choose the right tool for the job.
Okay. All right. Good. Anyone not get that needs help?
You want to try it?
Okay.
You should. Come on, try it. Go for it. But you're not going to be able to do it on many things if you don't try right now. See, look how many times you have to like see that. That's just so silly. Do you have a fraction button?
Yeah, I did.
All right. Any questions on this? Now, one of the things I need to mention is tonight in your homework, 90% of the homework problems use this formula. Now, your book's going to write it as something like P equals C e to the kt, so they use a big C here. just know that I don't expect you in your homework tonight to derive, come on. Ugh. 1 second. Computer. There we go. I don't expect you to derive this formula for every single homework problem, because you'd be redoing this exact same exercise, 20 times. So rather than doing that, you have my permission and blessing to use this formula whenever it applies, which would be for all normal exponential growth, all radioactive decay, all continuous compounded interest. All those problems use the exact same formula. But here's the catch. You will have to derive it on your quiz and your test. So you've got to be
Every
able
time?
to, well, there's only be like one of them, maybe
Oh.
two. So you have to be able to read a problem, write an appropriate differential equation, and then solve it. Okay?
Well, at least you know what the result will be if you get it right.
Yes, yes. Although I will tell you this, the AP exam, they love to do problems where it doesn't end up being a PERT problem,
That's
right? Yeah. We'll do one of those too today.
What horrible human beings.
Alright,
So-
alright, next. It's time to, we've done population growth, let's do some radioactive decay.
Score
Yeah,
of radium.
yes.
That's like
Let's
the
talk
least.
radium.
We should do francium. Francium's like the best element ever.
Is that just because you're from France?
No, it's actually a really fun element.
I like American.
Oh.
Or Californium. Stupid. I like
Californium.
It's an actual element, California.
Or just like nickel or iron. You know, iron is the last element created in the sun before it dies.
It's a man-made.
And then all the elements after that are all like after the sun explodes.
California.
Alright, here we go.
In fact,
The rate of decay of radium is proportional to the amount present at any time. If we call radium R, I want everyone to take a moment and see if you can write the differential equation for this problem. So the rate of decay of radium. Don't worry if it's growth or decay, just think change. The rate of change of radium is proportional to the amount present at any time. And by amount present, they mean the amount of radium present.
RDT
Yes.
equals
So,
KR.
the rate of change of radium is dr dt. Is means equals proportional to K times the amount of radium present at any time,
R.
R.
Radium, okay. Means variable.
All right, everyone go ahead and separate the variables. And then integrate both sides. And then solve for R.
And solve for R.
Yes. Did y'all separate the variables correctly? Keep the K with the T.
I put a little R.
Okay, you used lowercase r, that's okay. Alright, so we have ln r. Do I need an absolute value around this r?
No.
No, because you can't have negative amounts of radium. R equals E
I got it later.
C. R equals A E.
E to the C, there we go.
Is that okay? No question? No? Alright.
That's what it is.
Alright, good. Let's move on now. If 60 milligrams of radium are present now, and the half-life is 1,690 years, how much radium will be present 100 years from now? Alright, so I'm going to make a little T-chart here. T-R. So what time should I use for now? 0. So at time 0, we have 60 milligrams. The next piece of information we're given is the half-life. The half-life is 1,690 years, so that means when time is 1,690 years from now, how much radium will we have? 30. Does everyone understand half-life? It's okay. You got it? Okay.
You stuff it didn't actually fit it.
All right. Now the question, the thing we want to find is how much radium will be present 100 years from now. So,
Did you just see that?
oh, that was you?
I just made that!
That's awesome. Okay, when time's 100, that's what we're looking for, is how much radium.
That was so
Hey,
awesome.
give me a guess. If 60 milligrams are present now, and it takes 1,690 years to get half of
I'm
that,
gonna say 50.
Wait, I got this, wait.
57.
57, 58, pretty good guesses. All right, it's always good to have a little guess
It's
in your
gonna be
head so you know if your
43.
answer is reasonable.
43.
That's
Okay.
gonna be way off.
All right.
It's gonna be 43, I'm gonna guess.
All right, we'll see if you're right. All right, so we've got our, I'm gonna just rewrite the formula up here. R equals AE to the KT. So we plug in the first point, 60 equals AE to the 0, so our A is 60. Which makes sense, that's the initial amount. If you're using the PERT formula, you are welcome to just say, oh, my initial amount, just put it in. You won't always be using PERT, but if you are.
So it's better just to derive it.
All right. Next, when R is 30, T is 1,690. So we have 30 equals 60 e to the 1690 k.
And then, or divide by 60.
First, you've got to divide by 60. You have to isolate the e. So we have 1/2 equals e to the 1690 k.
ln.
Now we take the natural log of both sides. ln of 1/2 equals 1690 k. So k is 1/1690 times the natural log of 1/2. Okay? By the way, one of the things I'm hoping you'll start to realize is that k, for PERT problems, k is always the proportion of the amount that remains divided by the time it takes to get that amount. So if a half-life is 1690 years, k is ln of 1/2 divided by 1690. In other problems, you'll see something like it'll say the population takes 10 years to quadruple, then you would have 1/10 ln 4. It's the proportion of the ln of the proportion of the amount that's remaining divided by the time it takes to get that amount. You'll start to see that. You can just derive it every time, it's fine, but just so you know, you'll start to see that. So our formula is R equals 60 e to the 1/1690th times ln 1/2 times t. There's our final function.
Yeah, that. I don't know. Yeah, let's just.
We want the amount of radium that's present when T is 100. Something, I threw some people off this morning, and I want to make sure you understand a little concept. This is just a side mathematical concept. I can call the function R, or I can call the function R of T. R is the name of the function. If I write R of T, that's the same thing as R, just with a little more information telling you that T is my input variable. So if I call a function f, or if I call it f of x, those are the same thing. It's just that one is telling you that f has an input variable of x, but one is just calling it f. The function's name is f, either way. So, because I did something this morning, I said if I want R of 100, and a lot of people got thrown off and thought I said that I was doing R times 100. This is not R times. This is just R of 100, meaning we're going to plug 100 in.
Can we just give me an example of that? Write all these decimals down.
Well, how many decimals do you need to round to?
All of them.
With final answer, you only have to round to 3.
Okay.
Okay? So here we go. We have 60 e to the 1/1690 times ln of 1/2 times 100.
58. I'll round up 58.
57.58.
What is it, 57?
589.
589, and if you put 0.6, you would be wrong. Right? Because how many decibels do we always round to in this class?
3.
3, right? Yes, and
When were you saying we were not allowed to round?
anytime before the end of the problem.
Okay.
Especially with K, is what I was really saying.
Okay.
K is the most, K for common, K is the most common thing that kids make mistakes on because they round here and then it gets messed up by the end. Okay, any questions on radioactive decay?
Yeah.
Let's do, oh, yes?
How come like you can use for formula for this one and it still works the same way as if you were to use like the half-life formula?
I don't even know what the half-life formula is.
Like
I would have to look up the half-life formula and see how they relate.
it still works. I got the same answer.
That yogurt still
It gives you
The milk must come from
Okay.
cow angels because it is
We'll
so
do that,
perfect.
I will check on that for you,
Emily
but I got it, let's
That
finish
yogurt
this first
perfection.
and then I'll check on it for you.
It's a real tweet right there.
That grams good.
It's been way too long
You like
since
it?
I was out of, is it chemistry where you do half-life?
What round is
You
it?
sure?
Chemistry.
yogurt more than once a day.
Have you already
To
had your
know the
yogurt?
half-life formula.
I like yogurt, but it's not that much.
I would eat yogurt, it's about how many yogurt in my fridge.
Okay,
No, it's not ice cream, it was frozen yogurt. You know, it's a quart and a quarter.
You ever eaten
Quart and a half.
expired yogurt?
Have you ever had coconut yogurt?
alright, we're gonna change this last example a tiny bit.
Delicious.
This says, in a certain culture where the rate of growth of bacteria is proportional to the amount present, the number triples in 3 hours. We're gonna change this to say the number triples
Probably-
in 4 hours, just so that we don't have double
Probably
threes.
Roswell, you know, they're
I wanna make sure you're
disgusting.
clear on which is what.
Double three.
Everybody got the joke?
Okay? So everyone please change it to say the number triples in 4 hours.
Nobody got the joke, like,
Alright, so now we have the rate of growth of bacteria is proportional to the amount present. Whenever you have the rate of growth of something being proportional to the amount present at any time, that's PERT. So I'm going to call, so let's go ahead and write it. How do I write the rate of growth of bacteria? dB dt is proportional to equals K times the amount present would be B. Real common mistake is put T here. It's not T, it's B. The amount of bacteria present would be B. Okay, so now we divide by B. And we multiply by dt. And we integrate. And we get ln B. Be careful, because in this context, again, you can't have negative bacteria, but there will be problems you will encounter where you will need the absolute value. But remember, you can always just drop it and move it as a plus or minus to their side and just change your constant. So anyway, kt plus c. So we have b equals e to the kt plus c. b equals ae to the kt.
Are you allowed to like skip that step?
In your homework tonight, you can skip it.
Or for like test purposes?
For your quiz and your test, I'm actually, like part A makes you write the differential equation and solve it for B. So you're gonna have to do it. I make you do it.
thanks.
Oh, you're welcome.
That's gonna make it less likely that we mess up.
That's right.
Gives you good practice for the actual test when you do have to do it.
All right, here, a little knowledge of how the formula works will help you. So let's just talk about this. The amount, or the number of bacteria triples in 4 hours. At the end of 12 hours, there are 10 million bacteria. How many are present initially? Well, initially would be times 0. We don't know how many there are, but I can tell you in this formula, there's a letter that represents it. Which of these letters represents the initial amount? A. Put an A there. The reason we want to do that is because in 4 hours, the number triples. So when t equals 4, we're going to have 3a, because it'll triple, 3a, 3 times whatever the initial amount was. Does that make sense? Okay, and then the only solid data we have is that when t is 12, we have 10 million.
Would you wanna write out interest?
You could do 10 and then million, put the word million, but you have to be careful not to drop the word million.
Okay, but if you made it 10, would that affect your A values?
It would be in millions, so it would be the same, just smaller numbers, and you'd have to write in millions.
We ready to sig figs?
So, we don't need to get into that. Okay, sig figs. All right, here we go. So, so A is your initial amount. So let's plug in the next thing that we know. So when t equals 4, our number of bacteria is 3a. So we get 3a equals ae to the 4k.
Cool.
When we get that, what happens with the a's? They're gone. So we have 3 equals e to the 4k. ln 3 is 4k. So k is 1/4 ln 3. And again, remember, this is the proportion of the amount present, right? The amount that remains divided by how long it takes to get that amount, right? We have 3 times as much in 4 hours. All right, so now we have B equals AE to the 1/4 ln 3 times T. All right, do you want me to write 10 million or do you want me to write 10 for B?
10 million.
10.
10M will just confuse me because then I'll see an M and think it's variable. Just 10? All right, let's go 10. 10 equals AE